Hi, how are you? Hope you're keeping well. So we've given ourselves this task here that would help us go through an optimization task. What we can see is we have someone needing to make some judgment or decision amongst 6 different projects. How do we go about making the right decisions in terms of maximizing the expected net present values for the next 3 years? So what are we talking about? We're talking about the sum of cash that will be left over after we've paid out all the relevant outflows for each of these projects. Okay, so if we subtract the outflows from the inflows and we discount the net sums to the present value, okay, because remember, a pound today is not the same as a pound tomorrow and next year and year after. So we are discounting the net cash flows to their present values for each of these 6 projects. And you can see we have the NPVs here, right? So for project 1, we have 280K all the way through to project 6, where we have 360K. The issue is each of these projects require different sums of capital to be invested. So you can see for each of the next 3 years, we've been given the amount of money that would go into managing each of these projects, right? So that is a constraint. Why is that a constraint? For example, we've been told that even though these are the capital requirements, so for example, for project 1, in year 1, we have 180K, year 2, 160K, and year 3, 100K, and so on and so forth. We've been told that the decision maker or the firm has only £600,000 to invest each year. So why is that a problem? That's a problem because if you look at year 1, for example, if we add all the capital requirements together, let's see if we add them, mental maths. If we add them together, it comes to 1.2 and 10. So 1,210 at 1.2 million and 10. So we can see that exceeds the 600K. We need twice the amount of money available if we want to undertake all these projects. So we can't, right? So we need to optimize, and optimize then means we need to find the best projects out of the lot. Which ones should we go ahead with as we seek to maximize the return on those investments? Okay, so there's shortage of capital and we have to choose wisely. Effectively, that's what optimization is about. When you have constraints or when you have limitations, you have to be rational in terms of picking the options that will give you the highest return. So how do we go about doing that? We would go through the 3-step process. So we will set this up in a way that Excel can play with. By the way, I hope you've switched on your solver. So you can see, if you look on my screen here, I've got solver right there in the corner. And how did I switch it on? If you remember, if I went to File and I went to Options, come on. So File, Options, mine is switched on, so it's playing up. Anyway, so I hope you've switched your solver on, because we will need solver to set this up. So you should have gone to File, Options, and then you go to Add-ins. Add-ins will pop up, and then you click on the Add-ins, and then you switch on solver, and the data analysis to pack because you need them very much for this module. Anyway, so let's go ahead. So to set it up, we would normally look at the decision variables. So if you remember, decision variables are the options that we are choosing from. So in this case, that will be the project. So we have project 1, project 2, project 3, and so on and so forth. So we just simply typing that out, and then we have project 6. So they will constitute our decision variables. We are choosing amongst them. If you remember, I normally like giving each of these a different shade of color. Why? It's cool on the eye, isn't it? It helps you to distinguish between the options. So why not just give it different colors? Which one? I can try this one. That's close enough to the other one, but hey, let's choose that one, and then maybe we finish off with an entirely different color, which would be that one. Yeah, that's fine. Okay, so those are the decision variables, and then we would need to have the optimal values coming in here. All right, so we'll leave that row there. Let's give it a different color there. Highlight it out. This is where the system will spit out the solution, isn't it? So it's going to be blank for a long time until the solution pops up. And then we have the maximization objective. So we want to get the most out of the NPVs. So we just have to state the NPVs for each of the projects under the respective columns. So 240 for project 3, 160 for project 4, 400 for project 5, and 360 for project 6. And then we need to insert a formula here, and that formula would enable us to know the total NPVs that we would have after we've selected the optimal projects. Okay, so remember we use a sum product function. So we type sum product, and then we select the blank optimal values row, and then we use the absolute referencing, isn't it? Absolute referencing, do you remember? So absolute referencing is where you want these values there, these values that would pop up in the optimal values row to be constantly multiplied by whatever comes next. Okay, so what comes next is now the NPVs, which are the individual objectives for each project. So for now it's 0 because we haven't found a solution yet. And if you were guessing, the reason why we use the absolute referencing is we want to be able to drag that formula down, because remember we would have some constraints and we need to model those constraints. So for now, let's hold it there. Right, and then we come to our constraints. So our constraints could be many. In this example, we have just one constraint, and that is a constraint of available capital. So capital available. Available in year 1. And then we have capital available in year 2. And we have capital available in year 3. okay, just to help us. So we're just going to state the requirement for each project. So in year 1, we require 180 for project 1, and how much for project 2? 270. How much for project 3? 320. And then we have 60 for the next one, and we have 100, and then we have 280. Okay, so there is the need to state how much capital is available, right? We will just skip that bit in there, that cell. We come to the other side and say we only have 600 available. Okay, so for year 1, these are the respective capital requirements, and the sum of the constraint available, the resource that we require, the total bulk that's available is 600, so it's on the other side. We do the same thing for each of the other years. So we have 160, 160, 150, 120, 150, is it? Hopefully it is. And then we have 100 there, and again it's only 600. It's a fixed capital availability, isn't it? Final year, we have final year for project 1, we have 100, we have 120, we have 100, we have 80, we have 60, and 260. Hopefully I haven't mistyped any figure there. So that's how you set up your constraints. You look at the resource requirement for each of the decision variables, and you just slot it in under the right column. Now we can drag that formula down. Okay, so what we're saying is we know the formula here, right, would multiply these capital requirements by the choices that will be made here to tell us the total capital that we would use for year 1 in there. It will do the same thing. It will multiply the numbers in here by the 1s and the 0s that would pop up in the optimal values row to tell us the total amount of capital that we would be requiring for year 2. Let's put 600 there. Okay, and then that would enable us check if we have stayed within the constraint. In fact, why don't I just move that here? If I move this column here and let's call it the maximum constraint, and then I can just type in here less than or equal to, right? Effectively, what I'm saying is the total figures here, the total figures that will pop up there, right? Total figures that will pop up for capital requirement for year 1, for year 2, and for year 3 should be less than or equal to the 600,000 that's available. Okay, and the way we would work that out is the function or the formula here will be multiplying the 1s and the 0s that will pop up in our optimal values row by the capital requirements for each of the respective projects. Okay, please remember, this is just for my convenience. I've written these operators here just to remind myself that the figures on the left right here should be less than or equal to the figures on the right, and that is not part of the solution. It's just there to give me a prompt. So what have I done so far? Let me just rehash what we've done. What we've done is we've translated this story here into a model, and the model has 3 key elements. It's got the element of the decision variables, the optimal values, which would be the solution, and the constraints, including the objective. Okay, so we simply stated the individual NPVs, which are the bits we want to maximize for each of our decision variables under the right column. We had to use a sum product function to bind the optimal values row and each of the individual NPVs here, so that we can find the total net present values after we have found a solution. So that row still remains unknown. And then we stated the constraints in terms of capital requirements for years 1 through to year 3. Because we use the absolute referencing for the sum product function here, we were able to just drag it down, auto fill, not forgetting to show the total capital available for each of the years. And that is a setup. So we can then translate or copy this into solver. So we go to our data and our solver, and when we do that, we just have to just pick up the figures for each of the cells that are relevant. So the first thing is, which cell represents the objective that we want to maximize? It's that one, isn't it? It's cell H18. So we just click, drop down the menu and select that for the maximization. The objective is to maximize, so we don't need to change anything here. We have to drop in the optimal values, right? These optimal values will have to be dropped into the by changing variables row here. Okay, so if you just notice what we did, we copied from B17 to G17. And then we need to upload, or if you like, bring in the constraints. We can do it individually, but because these three are all less than or equal to constraints, we can just add them together collectively like so. So on the left side of this menu, we can just bring these guys in and make sure that we've selected the less than or equal to. Why are we doing that? We're doing that because this is the maximum. These are the maximum sums of capital. So what comes up or what shows up in here cannot be more than the maximum. Okay, and then we go to the right and we select our total capital requirements. We say okay, and we're almost done, apart from we haven't told solver that the optimal values here should be binary. So they should be 1 or 0. 1 means yes and 0 means no. So we have to add another constraint, and we select these guys again. We click on that drop down and we say they should be binary, bin. Okay, we say okay. Got an error message pop up. Binary constraint cell reference must include only variable cells. Okay, so what's that? Let's just do this again. I think when we copied this, we needed to just let it be that, and then we said just add and see what happens here. That sorts it out. I don't know, there was a glitch there, and I'm not going to edit this anyway, so I hope you just realize, I think I had copied the wrong cell somewhere. Okay, so yeah, we just have selected the optimal values rule again, and we've made it binary as a constraint. And then we click on solve, okay, and then it will solve it. Let me just go through this again. Maybe what I do, why don't I just delete everything and do it again, so that we don't have any doubts, especially because of that glitch that popped up there. I don't know what was happening. Okay, so let's do it again. First thing, once we have switched on solver, is to pick the objective cell. So what are we seeking to achieve? We want to maximize the NPVs, and the cell for that is here. So we click drop down and select that cell. We are maximizing, so we don't need to change that. If we were minimizing costs or minimizing something else like accidents or whatever, we would have selected minimize, but now we are maximizing. Next, we pick our optimal values blank row, that one. And then we have to add that same row as a binary constraint. Why? Because we want Excel to tell us whether we should go ahead with that project or not. And the way it speaks to us is to say 1 for yes and 0 for no. So we go bin for that, and then we add these other constraints that are hidden in there because we dragged down the sum product function. So these guys on the left cannot be more than, so it should be less than or equal to these guys on the right. Okay, so we go okay, and then we solve. And once Excel finds a solution, it will tell us it's found a solution, right? So let's see what solution is giving us. It's giving us a solution of going ahead with project 1 and not going ahead with project 2, 3, or 4. We can go ahead with 5 and with 6. And why has it made these choices? It's made these choices because it's telling us that, look at the capital requirements. These are the sums of capital that we will be using in each of the respective years. So in year 1, we would use 560 out of the 600. In year 2, we'll be using 410. That means we have some slack, a bigger amount of capital unused. And in year 3, we have a bigger amount of huge sums of capital that we're not using. The reason why we couldn't go ahead with all these is if you add them to the picture, then in each of these years, right, we'll be going beyond the 600K. So given the capital requirements of the 6 projects and given the money available, we will be able to maximize our NPV by having 1,040,000 by choosing projects 1, 5, and 6. And because we have some slack, maybe we can decide on what to do with that capital to keep ourselves going. So I hope that was a quick intro for you. And if you have any questions after you've watched this, drop me an email. Let's go on to the second example, which will be similar, but with maybe 1 or 2 things added to the picture. Right, so we have a similar setup here, and I wanted to talk you through this. So this time we have 4 projects. We have the NPVs, and we have the capital requirements as usual. But what I want us to realize is that we can begin to analyze this scenario ourselves before we we put it through solver. And how do I intend us doing that? I want us to see that we can find the total capital requirements for each of these projects. So for years 1 through to 3, we can add up the capital requirements. And if we added up the capital requirements for project 1, you can see over time it comes up with 250. For project 2, 130, 260, and 330. Okay. And we can also look at the total capital requirements for the entire business for years 1 through to year 3. Why do we have a constraint? Well, in our minds, we're saying that the projects are taking this amount of money, but the business has only 300K. Let's just say the business has only 300 available to invest. So what do? There will be a problem in years 1 and 2, because if we went for all the 4 projects, you can see we are exceeding our capital availability. Unless we can have more money coming in, we wouldn't be able to do all 4. So we need to make some choices. And that is quite common in business, isn't it? You have so much. I mean, you can't have unlimited resources. So that is a problem. So on this occasion, what do? How do we go about optimizing? How do we go about choosing from amongst these 4 whilst we maximize our NPV and stay within the constraint of only having 300 available? Okay, so before we go into modeling in solver, why don't we just think about it in a very rational way? So what we can do is we can find the return on investment, right? So for project 1, we're going to commit 250, project 2, 130, and so on and so forth. Okay, so we know the capital requirements. So we can calculate the return by comparing the amount of money that goes in with the amount of money that comes out. So this is what's coming out. Bang, this is the output. Or these are the output, I should say. And these are the inputs. These are the monies we are committing. Okay. So we can find the return or the productivity or the efficiency by dividing what comes out with what goes in. And if we did that for each of these 4 projects, we can see the returns like that. And then we can rank them. If we put in a pound here, how much returns from there? We can rank them on this basis, because project 4 gives us 1.3 back, project 2 and 3 gives both give us 1.23, and project 1 gives us 1.08. So we can rank them thus, right? Project 4 gives us the highest return, 2 and 3 intersection, bracket, right, doubling up, and the one that ranks last is project 1. So even before we put it through solver, we probably would have just said, let's just go for 1, 2, and 3 and check to see if that would enable us meet our capital requirements. And I guess it would. So that's the intuitive understanding here. But the beauty of solver is we can add other constraints into the mix, and with a model we can check to see the effect of these constraints. So I'm just going to add one more constraint, and let's say, what constraint can we bring up? Let's say on this occasion we were going to select both 3 and 4 intuitively, but what if we have to only choose one of 3 and 4? What effect would that have on us? So let me just delete the solution now. I hope you haven't looked at the solution yet. Let's just delete it. Go away, solution, clear that. And what else? Yeah, everything else can stay. Everything else can stay. I'll just talk you through that. So if we can only choose one of 3 and 4, right, how would that change the picture? Right, okay, so maybe get this guy out as well. And okay, so let's start the modeling. So these are our decision variables, and these are the choices that we have available. We have to choose between projects 1, 2, 3, and 4. Optimal solutions will come up here, right? Solver will tell us what the optimal solutions are. Okay. And we have our NPVs 270, 160, 320, and 440. Okay. And then we have our constraints. We have year 1, year 2, year 3. These are the capital requirements, right? I hope I've typed them in properly. Let's just check, right? So for project 1, I've got 70, 50, 90, 110. Good. And then year 2, 120, 40. Oh, there you can see, made a mistake there. So 120, 40, 110, and 100. Good. For year 3, I have 60, 40, 60, 120. Excellent. And after I've typed in those constraints, what do I have to do? I have to use my sum product function. So I type my sum product and I bind the blank optimal values rule with the objective unit, and then I just drag them down and just check to see. Let's just check to see, yeah, that. So I dragged it down so that each of these rows here will be multiplied by the optimal values rule, right? Just check each one like so. Good. And then we remember that the total capital available for each year is 300. Please remember we've made that up, okay? So we've got 300 there for each of those years. And the type of problem we have will be a less than or equal to. Okay, so I'm just typing that in there for convenience. And then we go into solver and we model this first, okay? We want to check what the effect will be if we just have these capital requirements. And then remember, we would add one more constraint that says between 3 and 4, we can only choose one to see what the effects of that will be on the solution. So if I go into solver now and clear whatever I have there, let me just clear whatever solutions I have there. Just putting this up on Moodle, so I already have the answers in there. Good. So we delete all of that and we start all over again. So the objective is to maximize this, which represents the total net present values. Okay, so we maximize that. And then the optimal values, right, that needs to change or that need to be modeled are there. And then we add that same row as a binary constraint, remember. And then we add all of these here as less than or equal to the total capital requirement. We say okay, and we solve. So when we solve that, if Excel finds a solution, it will tell us. And good, lo and behold, can you see Excel or solver is saying we should, on the basis of the information we've provided so far, we should only go ahead with projects 2, 3, and 4, which was the solution we found here when we looked at the return per project. Okay, so project 1 brings us the least, and because we have just 300k available, we should spend it on the last 3 there. Now let's add one more constraint. So what if for some reason we cannot go ahead with 3 and 4 at the same time? Let's say they are substitutes, right? They are kind of, there will be some cannibalism, like serving the same purpose or appealing to the same customer set. So we don't want to go ahead with both of them. We have to choose one or the other. So if we throw in that constraint, say either 3 or 4, how do we model that? Well, 1 is for yes. So if we say yes to 3 and we say yes to 1, we will have an issue, right? Because we can only say yes to one of them. So the way we tell Excel is we'll say to Excel, you can only choose one of these two. So 3 and 4, sorry, just typed that in wrongly. Right, 3 and 4 can only be 1. Right, so these two here, well, they are 2 now. You are being forced to choose only one of them. And the way we would just check now, so I've just dragged the sum product formula down. You can see now that that is 2, but we want that to be 1. Okay, so we would go into our solver and add one more constraint. We will add this constraint here and say, but that should be forced to become 1. Did you get a picture? So yes, yes, impossible. It can either be yes or no, or yes or no. So if we just say okay now, we can ask solver to solve this, and let's check to see if that solution there will change. Well, it might change, because if we're only choosing one of these two, then that would probably free up the capital for us to invest in project 1. Let's see if that's the solution. So let's ask Excel to solve. He's found a solution. He's found it. Excel, what did you find? Bingo. Well, we are not surprised, because project 4 has a higher return than project 3. So Excel has gone for 4, and because we can only do 3 or 4, has dropped 3, and the amount of money available now enables us to go for project 1. So these are 2 hopefully quick examples that I hope would give you a good intro, a good understanding, an intermediate awareness of how to go about translating your problems into models, and how to use the solver tool pack to model each of these constraints and to reflect on changes to the optimal solutions. All the best.